Hi everyone. This is the second Graph 3 lecture. Let's get started, I guess. Sorry about the technical difficulties, by the way. It was unfortunate. Joe, you're the clicking. I can't click. Okay. So the first topic we're going to start with is Dijkstra's algorithm. Um, and the goal of this algorithm, the problem we're trying to solve, is that we're given some weighted graph. This can be directed. It doesn't really matter. And some starting vertex S in that graph. And we want to figure out how far all the other nodes are in the graph from S. Remember that for an unweighted graph, we were able to just use a BFS, where we just keep on branching out one distance away at a time, and then when we find our final node or all the other nodes, we know how far away they are from the starting node. That doesn't work for a weighted graph, because it might be good to take a bunch of small weight edges, rather than a single big weight edge, and it becomes very confusing to do anything like the BFS idea for this. But so we instead want to use Dijkstra's algorithm. Okay. Um, okay. So the main idea for Dijkstra's is that we want to go in a bunch of steps, and at each step we take the vertex that has minimal current distance away from the start, and then we update the distance for all its neighbors. And then we sort of ignore that, vertex from then on. So the vertex that I said we're gonna fix, we update all its neighbors and then just let go of it forever. Um, so I think it's being very clear if I do an example for the graph we're given. Um, so initially, what we do is we set distance a equals 0, because a is our start vertex. So we just start with a equals 0. Okay. And so A is the first vertex we haven't visited, right? It's the closest one, because uh, it has minimal current distance because it's 0. Nothing else is 0, right? Then we look at both of its neighbors. In this case, it's B and C, right? So then we update their distances as if when they go through A, right? So C is 1 away from A, so it's 0 plus 1 is 1. B is 3 away from A, so it's 3 plus 0 is 3. And then so we update their distances, right? Then we don't consider A from now on. We ignore A for the rest of the problem. Okay. Now, next step, we look at, okay, now who has the minimum current distance now that we're ignoring A? Okay, it's C, because C is 1 versus B is 3. Okay, so now let's look at the neighbors of C. Okay, well, C to B has a distance of 7, right? So that puts us 1 plus 7 is B's distance of 8 away. But for B, we already had a way to get to it with 3. So we don't want to go through it from C, because that takes 8, so that's bad. Um, However, for D, we had no other way to go through it, so we do 1 plus 2 equals 3. So D also has a distance of 3. Then for step 3, we repeat on B. So if we take node B, and then we look at its neighbors, D and E. E was 3 plus 1 equals 4 away now from A. Whereas D was 3 plus 5 equals 8, so we don't use that. We just go through C like we were before. Finally, we look at D's neighbors, which is E. It's the only guy we haven't visited yet. However, again, that same thing. 7 is really far away from just 4. So we don't take that edge, but we maintain E's original path. And so now, after we process all the nodes, we're done. We would process E in this case, because E is also not visited yet, not being ignored yet. But it had no unvisited neighbors, so we just do nothing in that case. And so in this way, we found out how far away everything is from the node A. Any questions? Any example? Or like what exactly I'm doing at each step?
So one thing is you kind of want to think of initializing all of your distances to like infinity or some really big number. So that way in the beginning, uh, you would pick your source vertex because that has distance 0. Everything else is distance infinity. So that one has the smallest distance.
Uh, yeah. And the oh sorry. Okay. I'll get more into the exact implementation in a second. But yeah, I guess we go to the next slide and I'll explain exactly what's happening. Right. Oh yeah. So before the implementation, I want to show why this is correct. Why this works, right? So when I'm talking about ignoring these vertices from then on, we maintain some sort of visited array, like we do for DFS, or like used or visited, right? Um, and so when we process some node, which has a minimum distance so far, we do all its neighbors and we mark it as visited. Okay. So when I'm talking about minimal distance, I'm talking about the unvisited node with minimal distance, right? So the trick here, the really critical trick, is that we're assuming all edges have positive weight. I guess I didn't mention this up front, but that is the assumption for Dijkstra's. That we assume that distances are positive. Um, in that case, the minimal unvisited node we know has its current distance to be the correct current distance. Its correct distance is the final distance for it. Because any other path, right, that would go through some other unvisited node would only have a bigger distance. Because A, it would have a bigger minimal like current distance, and then B, you'd have to take another edge to further increase the distance. So that could only ever be worse than your current distance. And since there's no other node who has smaller current distance than you, this node will never have its current distance updated to something smaller. So its current distance may as well just take it as the final answer, right? So we take it the final answer. Then we can use this to update other nodes. So any path that goes through that node, right? So if you start, like, for example, look at B, right? If B is our current thing that we're fixing, right? The minimal distance guy, all of its neighbors, any path that goes through B will use this final distance as its answer. There's no point in waiting to update all the other guys for their path through B. So then we just use that to update all its neighbors. And that'll also be correct. And then we can just mark B as visited because we know we have its final answer. And then for the rest, and then we keep on just iterating and keep on marking nodes as visited as we go. So how to implement this, right? So if you just had a list of all the nodes, right, and their distances, and each time to find the minimal such guy, you loop through it, that would be n squared. Which itself is not that bad. It doesn't blow up like as bad as I'm saying, and the reason for that is the visited array. So each time we mark some guy as visited, right? And each iteration we do two things. We first find the minimal guy, and if we're just looping, we're doing a loop for that. That would take on steps. Then we look at its neighbors, right? And then we mark it as visited. So we only process each node once because we're marking it as visited, and then at each step we only look at its edge at each of its edges once. So across all iterations, we only use each edge once. This is similar to DFS. So that's sort of M uses of the edge. M sort of taking the edges, and then for each node, we sort of do ON work to find the minimal current distance. So that'd be like n squared plus m. However, we can use something better data structure here rather than looping. We can use what's called a heap or a priority queue. In data structures, you guys must have seen this. What it does is it lets you store a whole bunch of objects, and then it lets you find the smallest such object from the thing very quickly in login time. It lets you find the smallest one in O1 time, and lets you use it and pop it off in login time. So what we do is we construct this priority queue on pairs of. Oh. Okay. I don't know. I'm not sure what to do with the audio. Okay, cool. So we take these a pair of the distance and the node, both will be just numbers, and we put them all in a priority queue. Okay. And then each time we want to find the minimal current distance guy, we just take this heaps pop method, right? Because that would get the smallest value, and the smallest value would correspond to the smallest distance, and then that would give us the node with the smallest distance. And then we would process it and do its relaxations and find the neighbors and update all their distances. And if we do update it, we pop it back into the heap. We push it back into the heap, because then they are up for consideration to be used also. The sort of thing is that priority queue adds a log factor. So for every node, we take log time, to find the smallest node, and then we sort of mark it as visited, so then we only do that n times. So the complexity would be m times log n. Sort of reason that it's not n times log n, it's m. M in this case being the number of edges. Is that because the way you implement this is that when you sort of update a neighbor's edge, you can push multiple nodes twice. The priority queue can hold multiple nodes twice, because when you let's say you update one node through node A. Let's say you take a path through node A and you update this guy, and you push it onto the priority queue. Then later you go through node B, and then update that same node. Then you would also push it onto priority queue, right? There's no way to remove arbitrary elements from the priority queue. You only remove from the top when you're actually fixing it. So in that way, you can have multiple instances of a node into the priority queue. And in fact, you can have the total number the size of the priority queue is the size of the number of edges in the graph. That's all it's bounded by. And each operation takes log time based on that. Yeah, sure. So priority queue is a data structure which really has two operations. It has a push, you push an object onto it, and it has a pop operation, which you find to pop the smallest object in the priority queue. And smallest in this case is just any sort of comparator like you for normal sorting. So in this case, a comparator would just be by distance. Yeah. C++ has this built in. It's also very easy to code yourself, but C++ also has it built in. Yeah, exactly. You need to have the constraints of the comparator are the exact same from sorting. You need to have an ordering, a weak ordering. So but in this case, everything is obviously sortable because you just have linear by distance, right? The sort of caveat is that we can't delete arbitrary things from it. Like we can't delete things from the middle of the heap. Only things at the top of the heap. And so what that means is that when you update a node, right? So let's say this node's distance was like 5 and is already in the heap with distance 5. Now we found a path to it that only takes distance 3, right? By one of our updates. Now we can't sort of update the guy in the heap. What we'll have to do is just push another element into the heap. This time with distance 3. So we'll have it show up twice in the heap. This isn't an issue for correctness because you always the whole property of the heap, and then it gets the smallest guy. So when you pop from the heap, you'll get the guy with 3 first before the guy with 5 distance. So you'll get the correct one. And then if you ever get one who's been visited already, you can just ignore it. However, this does mean that sort of the size of the heap increases to OM as opposed to ON, where again M is the number of edges. So the overall complexity is OM times log n. Across the lifetime of the heap, you'll be pushing and popping at most m items, but at any one time the heap only goes to size n. So operations takes log n, and there's m operations total, so it's m times log n. Any questions on like implementation or what's exactly happening? This is kind of confusing, I guess. Yeah, I can go over the example in the previous slide with sort of implementation in mind. Joe, can you go back a couple slides?
Yeah.
Yeah. Okay. So here, the priority queue starts out with just the single pair 0, A. Okay, and nothing is visited. Okay. And then what we do is we look at the priority queue and we pop from it. The priority queue only has one element, so we just get A. A is unvisited, so we're good. Okay, so everything is good so far. Then we mark A as visited, okay? And then we look at all of its neighbors. So it has 2 neighbors, B and C, right? Then their distances, as Joe said, start at infinity. And so 3 and 1 are less than infinity. So okay, so we did an update. Now that we did an update, we update their actual D values, but then we also push into the priority queue the pairs 3 comma B and 1 comma C. Okay? Now that iteration is over. Now we look at the smallest element in the priority queue. Okay, what's the smallest element in the priority queue? C, right? So we pop C off because we can pop the smallest guy off. Okay, so we pop C off. It's not visited yet, so we're good. Then we mark it as visited, and then we look at all of its neighbors. Its neighbors are B, A, and D. Okay, well A is already been visited, so we can't do anything. But B and D have not been visited, so we update their things. B doesn't get an update, only D gets an update, right? Because D is the only guy who actually gets smaller than infinity. B is not 7 is not smaller than 3. So then we push D onto the priority queue. We push the pair 3 comma D. Okay, cool. Now we look at the top of the priority queue again. Next step, we pop off B. And then now we look at B's neighbors, which are C, A, and D. C and A have been visited, so we do nothing. D has not been visited. However, we don't update it. We don't get an update out of it. And then we mark B as visited, and then so on and so forth until we're done. Does that clear things up? Okay, cool.
Okay, so the next algorithm we're going to talk about is topological sort. So basically the idea behind topological sort is you have a directed graph, and we want to basically sort the vertices such that every edge goes from an earlier vertex to a later one. So sort of skipping ahead to the next slide, one really intuitive example of this is, let's say your vertices represent courses and the edges represent prerequisites, where like if you have an edge from U to V, you have to take course U before course V. You basically want to know like what's one order you can take the courses in. So in this example, we're given this graph and we want to produce one of these orderings. And if we have a cycle in the graph, like let's say this edge was directed from 2 to 1 instead, then this would be impossible. We also have an edge from 2 to 1. So we have to have 2 before 1. So yeah, if we have cycles, then this is impossible. Okay. So basically, the idea here is we're going to do sort of a greedy approach. But before we get into that, just some quick terminology stuff for directed graphs. So we say that the
I got a question.
Oh, okay. Right. So by earlier or later, I mean like they're index in this sorted list, basically. Right. So like if you take any two edges, any two vertices that have an edge between them, like 3 and 4, 3 is earlier than 4 in the list, right? Because it has a lower index here. And we have the edge directed from 3 to 4, so that works. But let's say we had like, we moved the 4 to the beginning of the list, then this wouldn't work anymore because now we have the 3 after the 4, which is not okay. So like, again, going back to the class example, it's like if 3 is a prerequisite for 4, you can't take class 4 before class 3. Yeah. Okay.
One thing I kind of want to mention is that these topological sortings are not unique necessarily. You can have many different topological sorts for a single graph. The whole goal is we find some topological sort that works.
Right, so like for this one, it doesn't matter what order you take 5 and 6 in. Once you take these 4, you can choose to take these 2 in either order, and that's fine. We just need to get one of them. Okay. So yeah, back to the terminology. So we say the in-degree of a vertex is the number of edges that go into it. So like if you look at 2, we have 2 edges going into it. So the in-degree is 2. And then the out-degree is like the opposite of that. It's you look at the edges going out of it. So the out-degree of 2 would be 1, because we only have one edge leaving 2. And this doesn't really come up much in topo sorting, but in general, vertices with in-degree 0 we call sources, and out-degree 0 we call sinks. So for example, 1 has nothing going into it, so we can call it a source, and 5 and 6 have nothing going out of it, so we can call those sinks. So this comes up in, I don't know, like max flow problems, which is like a much more complicated topic. But basically, the reason behind this is you can think about it, the graph, as like water flowing between these edges. So this is like sort of the source of the water, and then these are the sinks where like the water gets drained away. That's like kind of the reasoning behind that. Okay. So back to the actual algorithm. Like I said, we're going to be doing it basically greedily. And the way we do this is at each step, we're going to find some vertex that we can take now. So that means it has to be a source, right? Because it has to have no edges going in. So like the first vertex you pick would have to be 1, right? Because that's the only source. Everything else depends on something else, right? Like 3 depends on 1, 5 depends on 4. 1 is the only one you can choose at the first step. So then the idea is we're basically going to remove 1 from the graph and remove all the edges that are connected to 1 from the graph, and then repeat. And then once we've removed all the edges from 1, what's our new source? So like what's the next vertex we can take? And so the way we implement this is you store a list of all the sources. So you initialize this to be just all the sources in the original graph. So you could have a bunch. In the example, we only had 1. But you could have a lot of sources in the graph. So you put them all into a list. And we also want to store the in-degrees of all the vertices. And so now what we can do is while you have some source in your list, just pick any random source, like let's say the first source in the list, and take that out of the list. And now what you're going to do with that source is first add it to your ordering, right? Because that's going to be the next thing in your ordering. And then what we do is we want to basically remove all the edges, although we're not going to actually do that because we can do it in sort of a nicer way. So what we do is look at all the edges going out of V to some other vertex. Let's say that vertex is W. What we can do is instead of actually removing the edge, we can just decrease the in-degree of W by 1. And once the in-degree of W hits 0, then we know it's a source. So then we can add it to our list. And you basically keep doing this while your list of sources is non-empty. And as long as you don't have cycles, this is guaranteed to add every vertex to your ordering at some point. And if you have cycles, what's nice is it's not going to like throw an error or anything. It will just terminate before it has visited all of your vertices. So you can also use this algorithm to check if a topological sorting exists at all, just by checking if your list is of size n at the end of this process. So does this idea make sense to everyone? Basically what we're doing is we're simulating removing the edges by decreasing the in-degree. Okay. So the code for this would look something like this. So you have your basically standard graph representation here as like an array of lists of things you're adjacent to, so your adjacency list. And in addition, we're going to store the in-degree of every vertex in this array indeg. And we're going to have these 2 lists, sources, which holds all of your current sources that you haven't removed yet, and topo, which is your final ordering. Okay, so we do basically the standard input reading for the graph. Note that it's directed, so we're only adding this edge in one direction. And also note that we are incrementing the in degree of v, right? Because we're adding an edge from u into v, so we increase the in degree by 1. And they all start off as 0 if you declare globally like this. Okay, so then what we do is we want to initialize our sources list. So basically all we do is iterate through every vertex, check if its in degree is 0, and if it is, add it to the sources. Okay, so now we have our list of all the initial sources. And then we're going to do what we talked about, basically repeating these steps while your source list is not empty. So we're going to take an arbitrary element out of this list. So in this implementation, we're taking the last element, so dot back, just because that's the easiest one to remove in C++ with a vector. And it's actually the only one you can remove in constant time from a vector. So yeah, we take the last source in the list, we add it to our ordering, because that's going to be the next vertex in our ordering, and then we remove it from sources. Okay, so now all we have left to do in this step is update all of the edges coming out of V. So the way we do this is look at all the vertices U that are adjacent to V, and then decrement the in degree, because we're removing that edge that goes into U. And then if the in degree is 0, we can just add it to the end of our source list. And so now at the end, if the size of our list is n, so if we visited every vertex, then the graph is acyclic, it doesn't have cycles, and we have produced a valid ordering. Otherwise, then we know we found a cycle and there is no valid ordering. Okay, so questions on this? Oh yeah, I missed all these questions. Yeah, so for directed graphs, all you do is you just don't add the edge in the other direction. Okay.
Perhaps one thing to mention with directed graphs is that a lot of the ideas from undirected graphs we sort of lose. We lose the idea of connected components and stuff like that. So it becomes less obvious. Like the algorithms become sort of maybe harder to think about, but the representation is pretty similar as just as Joe said. Just remove the pushback from the input.
Yeah, and a lot of times algorithms on directed graphs will sort of reduce to toposort in some way. So this is a really useful thing to know for directed graphs in general. Oh, whoops. Any other questions on this? Okay. So now we're going to talk about spanning trees. So a spanning tree is basically a set of edges within a connected graph that forms a tree that contains every vertex. So for example, if you look at the red edges here, these would form a spanning tree. Because if you look at just the red edges by themselves, that's a tree, because there's no cycles within the red edges. And they also connect every vertex. So it's like a tree and it spans the whole graph. And you can have many spanning trees for a graph. So for example, if we removed this edge from the spanning tree and then we added this edge, that would be another one, right? Because you can sort of visit this vertex through this edge instead of this one. And that would still be valid. Okay, so now for weighted graphs, we have the idea of a minimum spanning tree, which is we want to find the spanning tree that has the minimum total weight, where basically we're just adding up the weights of the edges within the spanning tree. So if you look at this example, these red edges would form the spanning tree because the sum of these is 18, and any other spanning tree you form would have a weight greater than that. And there's two main ways we can do this, and we're going to go over both of them. Okay, so the first way is Prim's algorithm, which is, I guess, kind of similar to Dijkstra's in like sort of the general way that you do it. So you're going to maintain a set of vertices that you visited. And basically the idea is you're going to sort of maintain this component of visited vertices and keep adding the vertex outside this component that has the smallest distance to something inside this component. So to start off, just have a set containing, like, say, just vertex 1, or any arbitrary vertex, really. And then at each step, you want to find the minimum weight edge between a visited vertex and an unvisited vertex. And then add that edge to your minimum spanning tree and sort of add that unvisited vertex to your visited set. And you're going to repeat this until all the vertices are visited. Okay. So it's probably helpful to see an example for this. So if we look back at this example again, so the red vertices are visited, and the red edges, as we add them, are the edges that will be in our minimum spanning tree. So we start off with just this vertex is visited. And what we're looking at now is the set of all edges going from a red vertex to a gray vertex. So initially we have 7, 7, 1. So the lowest weight edge there is the weight 1. So we're going to take that edge in our minimum spanning tree and add this vertex to our visited set. Okay. So now we're going to look again at all the edges between a red vertex and a gray vertex. So we have 7, 7, 6 here. So the lowest weight 1 is the 6. So we take that and we add this vertex. And then we're going to repeat again. So now we have a lot of edges. We have 2, 3, 4, 5, 7. Oh, wait, no, not the 3. We have 2, 4, 7, and 7. And so the minimum weight edge there is the 2. So we're going to add this vertex and the 2 to the minimum spanning tree. And now we have 4, 5, 7. So we add the 1 adjacent to the 4. 3, 5, 7. Oh, 2, 3, 5, 7. So we add the 1 adjacent to the 2. And then finally 3, 5, 7. And the minimal one there is 3. And so now we're done. And you'll notice that this is the same minimum spanning tree we had before. One thing to notice is it doesn't matter how you break ties. So let's say in your fringe you had like 2 edges of weight 2. You could pick either one arbitrarily, and it doesn't matter. Either one would give you the minimum spanning tree.
It might get a different one. Again, these are not unique necessarily.
Right. You could have multiple minimum spanning trees, but it would give you a spanning tree with the same weight, so the same minimal weight. All right. Questions on this? So implementation for this, again, we don't want to iterate through all of the edges at every single step to see which edges are between like a red and a gray vertex. So what we're going to do to maintain this is we can use a set in C++, which is kind of similar to what Akif was talking about with like a heap or a priority queue before. Basically, a set is a balanced binary search tree. So if you guys have seen binary search trees before, it's like a binary search tree, except the depth is guaranteed to be log n, because they do all kinds of like rebalancing and stuff. Like whenever you add something and it makes the depth of the tree too big, it'll shift things around and make it work. So if you guys have taken data structures, it's basically the equivalent of an AVL tree. I mean, the algorithm it uses is different, but it does the same thing. So yeah, basically what this lets us do is we can check if an element is contained in the set in log n time, and we can also insert things into it in log n time. Okay. So for a graph representation, this is like the weighted graph representation we talked about last time, where instead of storing your edge just as the vertex you're going to, you store it as weight comma vertex, because you need to store like both of these things. And then we read it in sort of in the normal way. You add the edges in both directions with the same weight. And then what we're going to do is you're going to maintain this fringe. And this fringe is basically storing the set of all the edges between the red vertices and the gray vertices. So what the pair specifically represents is, again, weight comma vertex. for every red to gray edge we have. So the way we're going to do this is maintain what's like the next vertex we want to visit, and also the total minimum spanning tree weight. So initially, let's say like the next vertex is 1. So we want to visit vertex 1 next. So now we're going to keep repeating this while we haven't visited all the vertices. So while visited that size is less than n, we're going to look at all the edges coming out of next v. So next v is the one we're adding at this step. And we're going to add all of those edges into the fringe. So note that some of these edges might be an edge from a red to a red, because we're marking a next v as red, but some of the vertices next to it might also be red. But we're going to sort of handle this at the next step. So yeah, then we're going to mark next v as visited. So basically color that red. And then we want the smallest edge that's from a red to a gray. So what we could do is just look at like the smallest thing in the set, which again, we can get in log n time. But the problem is, again, we might have some edges from red to red. So what we can do is keep looking at the smallest edge in your set. Right, so that would be fringed up again using a C++ set. And then fringed up again dot second is the vertex. So while visited.count that vertex, so while the vertex for your smallest red to gray edge is red, that means that this is not really a red to gray edge, right? Because that means it's the one on the other side is visited too. So we want to remove that from our fringe. So while your smallest edge is a red to red, we remove that. And so now if we look at the smallest edge fringed up again, that's going to be your smallest red to gray edge. So we want to take that edge into our minimum spanning tree. So we're going to add the weight into our MST weight and mark our next vertex as that vertex. So now we're going to iterate through again and look at all of the vertices adjacent to this vertex and sort of repeat the process until we visited everything. And as long as the graph is connected, this code will run properly. So the fringe will never be empty until the end. Questions on the implementation? Okay. So now we're going to get into the other algorithm, which is Kruskal's algorithm. And this is also kind of a greedy approach. So what we do here is we sort the edges in increasing order by weight. And then think of every vertex starting out in its own component. And now we're going to iterate through all of the edges in order. And if the two vertices of this edge are in the same component, then we're going to throw it out. Because if we added this edge, then that would create a cycle. Right? If they're in the same component and you add another edge, now you have sort of two paths between those vertices. One in the initial graph and one with just this one edge. So then you have a cycle between them. But otherwise, if they're in different components, we add this edge to the minimum spanning tree, and we join those two components. So again, we have an example. So we start off with the smallest weight edge, which in this case is the 1. And initially, everything is in different components. So we can just take that edge into our MST. And similarly, for the next few edges, like if you look at the 2s, like say this 2, again, it's connecting two components, so we can just add that. And same for this 2, and the 3 and the 4, right? Because these 2 are still in different components, even after we've added all these edges. And again, when I say components, I'm referring specifically to components using only the red edges. Okay, so we can add this 4 also. Okay, so now we get to the 5 edge. And we can't add this edge because these two vertices are in the same red component, because you can get between them using only the red edges. So that means we can't take this in our MST. So we're going to throw this out and mark it as blue. So then we get to the 6th edge. Notice that these are in different components. So we can add these. But now, again, when we're looking at the 7s, now everything is in the same component. because you can get to any vertex, get from any vertex to any other using just these edges. So that means we can't take these 7s because they connect 2 things in the same component. So the approach makes sense? Okay. All right, so we're not going to get into the actual implementation for this approach because basically what we need is some kind of data structure that lets you check if 2 vertices are in the same component quickly and join components quickly. So we need those 2 operations. And we can use a technique called disjoint set union to do this. So we discussed this in the advanced lectures a while ago, and we'll get to it here probably at some point soon. But yeah, so we're not going to go over the exact implementation. But basically, it's just doing what we did here using the fast component queries and component joins that you get from DSU. Okay. So before we move on to problems, any questions on anything we've done so far? Okay. All right, so the first problem is triangles. So you are basically stacking up n triangles, and you know the final positions. So you can sort of think about it as you like drop them in from the top, and you know where all of them land at the end. And it's guaranteed that every triangle is either sort of lying on top of another triangle, like you see 2 is lying on top of 1, or it has a segment on the x-axis. So basically, you want to know what is one possible order that the triangles could have fallen down to get the given configuration. So like in this case, they could fall down in the order 1, 5, 4, 3, 2, or 5, 1, 4, 3, 2. Oh, wait, yeah, so we did have a question. Yeah, so Akif answered it. So once you know DSU and you have like a good implementation, Kruskal is faster to implement because it is basically just DSU. But without knowing DSU, Prim's is probably easier to understand. Okay, yeah, so back to this problem. Anyone have ideas? So not even like really any specific implementation ideas, just like any ideas in general for how to solve this. So what would be one way you could represent this as a graph? Yeah, exactly. So if 2 triangles share an edge, we can sort of add that into the graph somehow. So okay, assume that sort of you can figure out which pairs of triangles share edges, and sort of any other like geometry stuff you would need to know for that. How would you want to set up the graph, like specifically, or what technique? Yeah, exactly. So the idea is you want to use topological sort, where your edges are directed from triangles to all the triangles that lie on top of them. So in this case, we would have an edge from 1 to 2, from 1 to 4, 4 to 3, 3 to 2, and 5 to 4. So anytime you have a triangle sort of lying on top of another one, that would be an edge going upward, basically. And now that just reduces the problem to a topological sort. And yeah, so where you like start off with the ones in the bottom, and then you basically go up from there, like the topological sort, like we talked about before. So the one sort of tricky part about this is like constructing the graph. So figuring out when to add an edge between U and V. But basically what you can do is like, given two triangles, check all pairs of their sides. So like all 3x3 pairs. And you can see if they lie on the same side, lie in the same line, and if they intersect. So that's basically like pure implementation. So we're not going to like go into that now. But then again, once you construct the graph, it's just toposort. Okay. All right, Keith, you want to take this next one?
So this problem is called castle, and so you're given a grid, n by m, and you want the number of rooms and the size of the biggest room in the graph. Okay, but the thing is, the graph is sort of given as this not graph grid. This grid is given in this sort of format, this text format, where you have either walls or empty spaces where you can travel through, right? So the spaces are the actual like positions in your castle. The horizontal like pipes or the dashes are spaces you can walk through, like hallways. And then the hashtags are the walls in your grid in your castle. And so a room is just like a connected set of spaces. So spaces where you can walk from one space to another space. And the question is, how many such rooms are there, and how big is the biggest room? Okay, so any ideas? I mean, the basic idea should be pretty obvious from if you came last week, but yeah, exactly. So we want to find connected components, right? Can you right? Yeah. So if you came last week, if you think of it as a graph, right, where each point, each sort of space is a node, and you have an edge. If you don't have a wall between two nodes, then we have an edge, right? Then we just look at DFS and find the number of connected components and the size of the biggest component, right? Pretty obvious stuff, right? However, the reason I'm sort of bringing up this problem this week is because of implementation. This is not unlike all the other problems we've done so far. This is not given in like the format we're used to, where they're given UV pairs and you sort of push back and all that, right? This is just given as like a bunch of strings as a text grid. So implementation will be slightly different, and I want to go over a nice way to implement this. So one sort of change is that instead of using for all our like arrays, like for example the visitor array, the used array, and all that stuff, we don't use single dimensional arrays because our nodes are not numbers anymore. There are two numbers. There's the x coordinate and the y coordinate, right? So now we use 2D arrays for all this, for x comma y, right? Additionally, we don't store our adjacency lists anymore. We just store the original grid. Joey, you want to the next slide? And so this is the sort of main part I want to bring up, and this is how you actually implement it. How do you actually make your own edges on the fly? So when so in your DFS algorithm or BFS or whatever you use, in this case DFS, you would write something like this. Here you would loop over all the possible deltas you can take. Deltas in this case being either up, down, left, or right, depending on these vectors or sort of like right. And you would look at your current x and y position, and you say, okay, I'm looking at the next x and y position, right? That can go by taking this delta. And if that is unvisited, and as you see, we're using this 2D visit array, and it's within the bounds of the grid, so it's not to the left of 0, it's not to the right of m, it's not below 0 or below n, and we can take that because it does not have a hashtag between them, then we continue our DFS, right? And so this is not an exact implementation of the problem where you would probably have to keep track of all the DFS stuff, like size of component or and do multiple DFSs from each component to calculate how many components. But this is sort of a main idea where normally you would just have like for V in graph U, right? This top for loop would be V in graph U, and we would check visited U. Here we would sort of want to do this thing instead, where we implicitly make the edges ourselves, as opposed to just being given the edges by the problem input. Everyone see what's happening in this code?
So in a problem like this, you could also represent it the normal way. Like you could loop through and sort of find all the edges between two squares, and then like make like a standard representation like with that. But the thing is, this is usually much easier to implement when you have a grid like this. Okay, so I guess we can move on to the last problem. So this problem is Detour. So you are given an undirected weighted graph where every node represents an intersection of roads. And every intersection has a sign that points in the direction of the shortest path to vertex n. And you can assume that these shortest paths to n are unique. But the thing is, you're not given the directions where these signs are pointing, right? So you know they're pointing, like let's say you're at vertex u. You know there's a sign pointing in the direction of the shortest path from u to n, but you don't know what that is. So what you want to answer is there a path from vertex 1 to vertex n that never goes in the direction of the signs? And if there is, find the path. So what technique that we brought up seems like it would be the most useful here? So like if you wanted to figure out what direction all the signs were pointing in, what's one way you could do that?
Any guesses? Like, even if you don't know exactly, I think it should be kind of obvious what the algorithm we covered.
This is tricky though, because it's like a sort of extension of technique we haven't really talked about. Okay, we can just go over it because there's a lot of non-trivial stuff here. So basically, what we can do is, oh well, yeah. So this is an example basically of what we want to find. So if this was your graph, your signs would be pointing in these directions, right? Because shortest path from 1 to 4 is that. Shortest path from 2 to 4 is that. Shortest path from 3 to 4 is that. And we want to know, is there a path that gets from 1 to 4 without going in any of the red directions? And in this case, there is, and we can go like that. And notice that you can travel edges of signs in the opposite direction. So like we could go in this direction, that's fine. Yeah, so that's basically the problem statement. So then to solve this, what we can do is we can do a Dijkstra's starting from vertex n. So we get the shortest distance to vertex n for every vertex, right? Because that's what Dijkstra's does. And then in addition, we can store some extra information, which is basically the parent of every vertex. So you can think about the parent of a vertex in Dijkstra's as the one that you visit right before it on the shortest path to the whatever your source vertex is. So for example, like going back here, the parent of 3 is 4 itself, the parent of 2 is 3, and the parent of 1 is 3. So you can think about it as if you have this tree that's sort of directed up to your source vertex, you're looking at the parents in that tree. So like if 4 was the root of the tree and you sort of shift everything around to make that work, then 4 would be the parent of 3 and 3 would be the parent of 2 and 1. So that's basically what we want to store. And the way we can do this is every time you decrease the distance to V, you can update parent of V to whatever vertex you just connected it to, right? Because every time you decrease distance of V, it's because you're looking at the edge from V to some other vertex U plus distance from U to N. So every time you decrease dist V, when you do that, you want to set the parent of V equal to U. And then after the whole Dijkstra's, parent of V will hold the best possible parent for V. So now V comma par V is all of the edges that you're not allowed to use. And now that you have a list of all the edges you're not allowed to use, to check if you can get from 1 to N without those, you can do like just a DFS or a BFS and make sure that you never go on the edge from V to power V for any V. So is this solution clear? The parent thing can be a little bit tricky. Anyone have any questions? Okay, cool. So that's it for today. Thank you guys for coming. We will have another graph theory contest on Wednesday, so we see you guys there. And yeah, we will have this recording up soon. So thank you guys.